Good evening, everyone. Thank you very much for sticking around for this talk. I'm really excited to talk about Clippy or SkyNet for your Security Operations Center. A little bit about me. I love solving security problems with data. And when I say I love solving security problems with data, I don't mean just machine learning or fancy deep learning. I mean everything: rules, analytics, statistics, machine learning, and deep learning. What I have done so far, I've delivered a couple of analytics, AI, and ML solutions for both security vendors as well as enterprise security teams. So I've had a perspective from both sides. What I really like doing is helping security teams succeed in adopting data-driven approaches in their security operations center. I advocate for risk-driven security approaches. I know a lot of focus goes on threats, but I really like concentrating on the risks and what makes sense to mitigate those risks. And finally, I'm an inventor on 3 patents, and I'm still a novice open source contributor. And just fun fact, I started my journey in Pittsburgh, my security journey in Pittsburgh, so I'm really happy to be here speaking at B-Sides Pittsburgh. I went to Carnegie Mellon, did my internship here, and of course, I love dark themes, as evident from my slides. So a quick show of hands. How many people have dabbled with data science here, or statistics? OK, good. I have the amazing right kind of audience. And how many people have actually implemented machine learning solutions in your security operations centers? Great. I definitely see one hand there. That's amazing. And was it successful? Oh, OK. Cool. Very cool. It's always good to know that people have at least tried to dabble with it and play with it. And maybe the other question makes more sense. How many people have seen failed machine learning projects? Great. OK, that's also great. We have all the right kind of audience here. I think everybody has seen this statistic. 85% of AI projects will fail through 2022. This was something that was told in 2018, and this has been the case so far. And this is not necessarily just limited to security operations, but also across all domains. But security makes it even harder, and that's because of the adversarial nature of our domain. And 90% fail before they're even started. And one of the reasons why they fail is because most of the times there is a mismatch in the problem that we choose, as well as the approach that we choose to try and solve that problem. And just like any other learning curve, I think one thing that I have found in my experience is that the moment you get your first machine learning solution working and deployed, it becomes much easier to deploy more solutions. And you kind of get a feel or hang of what would work and what would not work. Yeah, so today I'll talk about all the experiments that I have done in my career journey so far. And this is all specific to security operations. All the experiments are either decision support related or threat detection related. And what I mean by decision support is where you use analytics, machine learning solutions to help drive operational efficiency and to help the analysts make a decision, as opposed to making a decision for them. I'll also be talking or touching briefly upon the different kinds of solution complexities and why I thought one approach would work better than the other and in what circumstances. And then later switch gears a bit to talk about what it takes to build a successful data science program. And then finally wrap it up with certain takeaways, like what are some of the good, bad, and ugly things that I have seen. So I think that's what I'll wrap it up with. Another interesting thing that I wanted to touch upon in this talk is return on investment. Security operations as a whole has multiple moving components, and one such moving component is the risk appetite of a given organization. What amount of risk are we willing to take, and what amount of risk are we not willing to take? And how does that drive the bottom line for the operations as well? And what does it mean from a security or threat efficacy purpose? So coming back to the title of the talk, this is a slide where I have charted the complexity of the solutions along with the guidance that these different machine learning or analytics or any data-driven solution provides. So what I wanted to point out here is that, all right, I've charted this. Guidance is increasing from left to right, and complexity is increasing from top to bottom. The image themselves, I wanted to bring your attention to the images. The image themselves, they are generated by a recent advancement in AI and machine learning. This is called the DAL-E model. The DAL-E model basically takes a language input prompt and generates an image. So of all the things that we thought that AI would replace, I never thought artists would be one of them, or meme creators. Maybe our AIs will be creating memes as well. So the first image, the prompt that I gave for DALL-E was Clippy. And clearly, it doesn't look like Clippy. I mean, it's there. The outline is there. But for me, I don't know, it looks more like a stethoscope or, again, with some missing components. It definitely doesn't look like Clippy to me. And then I gave DALL-E the prompt of SkyNet. And SkyNet, this was an interesting picture. At least it was related. This is a picture of Terminator. I was expecting to see something else for SkyNet. Like, I was expecting to see the logo of SkyNet come up as shown in the Terminator franchise. So if anybody wants to play around with these prompts, you can visit crayon.com, and that's where the DALL-E creators have a backend provided, so you can just play with these prompts. A fun fact here as well, or just another thing that I was playing around. So when I gave SkyNet Helena Bonham Carter, it actually showed me a picture of Helena Bonham Carter with a cyborg-like image, and I thought that was funny, but I didn't want to put it here. It was not. It was an eyesore. Just coming back here. So I think I'm kind of foreshadowing already Clippy or SkyNet. So this DALL-E model is state-of-the-art. It has 16 billion parameters. So if you think about a straight line, a linear regression line, that's y equals mx plus c, that's just like one parameter. But this DALL-E model is 16 billion parameters. And when I gave Clippy, despite seeing a lot of words to image translations, I think this was the best it could come up with. So let's talk about the usual suspects. I like to call these the usual suspects because you must have seen a lot of these things in vendor talks. So what are some of the most common applications where we could leverage data to solve the problems in security operations? There are multiple problems here. So the first one is threat detection. Again, here, a huge umbrella under threat detection. So you can have malware detection, and outliers or user entity behavioral analytics. I think more recently the trend is to collect micro detections and chain them up into an attack sequence, because we all love MITRE ATT&CK framework. So that's with the malware detection aspect. The other data-driven solutions are decision support and operational efficiency. I think this is one of my personal favorites, because this is, again, helping drill down on the actual volume of data and alerts that an analyst has to weed through, as opposed to just coming up with and more detections, which may or may not necessarily be useful. So I think there are some really interesting use cases around the decision support. And then there's workflow improvements. Workflow improvements are typically trying to integrate all these data-driven solutions better with the tool chain that is in a security operations center. And there are a lot of playbooks that could be automated. And all of these are data-driven approaches. You don't necessarily need fancy machine learning. You can just look at some of the previous statistical dispositions, and you could come up with some good workflow improvements. Yeah, so Game of Thrones fans will probably know Trial by Death, Trial by Combat, and this Trial by Fire. And I think I have done the Trial by Fire, which is mostly diving deep into a lot of these experiments, and sometimes coming out unscathed, and sometimes being burned. So I'll briefly touch upon each of these quadrants. Like the first quadrant, threat detection. Like, what were some of the experiments that I did with threat detection at a very high level? And then I'll touch upon how do we automate some of the most common triage processes. I think earlier during the day, Alan and another gentleman was talking about how there are like so many alerts and events that somebody has to go through. So definitely, I'll talk about how do we how do we tackle some of the triage processes. And then the third one, which is presenting the right kind of evidence. So this is the critical part, and I don't think a lot of us have gotten this right yet. Most of the times I do see incident responders constantly trying to get the right kind of data when they need to make that decision and they don't have that information. And I think that's what analytics or any data-driven solution should address, provide the right kind of incident response evidence, like just provide the evidence that is timely enough. And then I think there's like this common decision support theme, so I can definitely cover that as well. All right, so the first one, the threat detection aspect. Yes, another iSource slide, but this is pretty old. This is a very simple obfuscation script, and this was when I was beginning my career around like 2016, 2017, when exploit kits were all the rage for the initial access as part of and delivering ransomware payloads. So exploit kits would typically break the browser system sandbox or escape that sandbox and try to launch malware, and most often that led to ransomware. So the first image here is just an obfuscated script, and the second image here is actually what it looked like deobfuscated. So I was doing a lot of this manually, and obviously nobody likes to do a lot of manual vulnerability research or exploit development. One of the things that I came up with was to see if I could, sure, I understand what the exploit looks like, I understand what the obfuscation looks like, but it's really hard to catch all of these things with very specific rules, especially when they're changing all the time. And they make very slight changes. Like, for example, you can see parent n plus ODE next to the script 0 in about the 5th line in the first image. Some other time, they'll probably change that into a different kind of string, and that makes it a little difficult to catch these things. So this is one example. And expert kits are gone now, but I can assure you that very similar tactics are still being used, especially when it comes to phishing and when it comes to a lot of PowerShell or AMSI script obfuscation. So obfuscation is a fairly common technique. So what are some of the experiments? Like, I think it's really critical to bring it down to a simple hypothesis or a simple problem statement. And the problem statement was, is this obfuscated or not? And in terms of gathering the data, we gathered a lot of benign data, malicious data as well. So we gathered some malicious landing pages. They were all labeled, fortunately, which is a boon, and that typically does not happen in the security space. We also gathered some full PCAPs just to look at what we can extract out of it and how that could help augment our models. The modeling was a supervised approach because this was the first way to start. We had the luxury of having labeled data. Again, it was a luxury, so really happy that we had the labeled data. Some of the challenges that we had was what we call in machine learning as class imbalance, which is a lot of data of one particular type, which tends to be benign, and a very small rate of malicious data samples, because the base rate of malware or malicious activity is less than 1%. In fact, I want to go out on a limb and say it's like around 0.05%. So that's what the base rate is. We had different approaches to address this. So we thought, let's try and generate data, because that could help us make a better model, because machine learning models typically do well only when they see equal samples. So cat or a dog, equal samples of cat, equal samples of dog, and they work brilliant. But in security, they don't, because we have this class imbalance problem. False positive reduction. This was something that was not a machine learning approach, actually. We used standard software engineering computer algorithms that could just help us reduce the false positives. And a lot of domain knowledge went into this in order to identify what could be a potentially malicious landing page. In a way, it's very similar to spam or no spam, because that's the kind of data sets that we are all used to, and that's the kind of data set that let us think that, OK, we can do more of machine learning in security. So if we're keeping score, the score here is Clippy 1, SkyNet 0, because we chose a very simple supervised machine learning, traditional machine learning model, and complemented that or augmented that with just basic traditional algorithms. So why were we successful? I think we were successful because the hypothesis was simple and it was specific. So it's really important to get that. And then the data is labeled, and it's in the order of millions. So that was another reason why we were successful. Coming back to the other quadrant in my slide, which was how do we provide the most relevant information for a SOC analyst who's doing the triage of the incidents, and how do we automate this process? Even here, the automation of this was it was a data mining approach, which has been there for a long time, ever since the invention of search engines. So we mine information from different logs and event telemetry, and we also used statistical approaches based that were leveraged as part of the rules and the past searches that a lot of these analysts who triaged did. So this was one way in which we gathered or mined all the locally available information. And then there were also a lot of other things that we can extract from logs. This is very traditional computer programming. Just get information about what was blocked, whether there were like some canary flights that were changed, whether a process actually ran. So these are some of the things. This is still a data-driven approach, because you're still using the statistical aspects, not necessarily machine learning and deep learning. And I think this is where the machine learning and the deep learning component comes into place. So this is kind of a moonshot idea where we thought, let's take this to another level. We have a lot of information that's available in the form of structured data that's in databases that we get from CISA bulletins or DHS bulletins. We get a lot of that data. We have a lot of other local telemetry that's also completely structured. But a lot of the time, SOC analysts also go look up blog articles. They read a lot. They do a lot of unstructured data. So we thought, let's take it one step further and automate this as well. And as you can see, this is like a blog excerpt during the WannaCry attacks that were happening. And we implemented some sort of a machine learning model that could help extract all these security entities. What I call as security entities are things that remotely look like security words, nothing like associated. It should mostly look like eternal blue, SMB exploits. So these are some of the security entities. And then there were also some timestamps and the relationship. So we wanted to extract all of this in an automated way using natural language processing. So as an example here, this is one successful example. So you can see that on June 27, 2017, the Petya ransomware may be spreading via the eternal blue exploit that was used in WannaCry attack from last month. And we wanted to present this evidence. And how did we do that? So we presented this evidence. So obviously, the ones that are explicitly provided in the blog article make sense. It's directly extracted using natural language processing. But there are some interesting statements there that said, Petya ransomware may be spreading via the eternal blue exploit used in the WannaCry attack from last month. And if you look at the timestamp that we provide, it actually goes back 1 month for the appropriate security entity and the relationship. So this is named entity recognition, standard procedure. But this was very interesting because this is one of the few successful cases where this worked. And it almost felt like leveraging this in order to make the automated triage process much efficient. It seemed like a huge operational burden. So these were, as I mentioned, these were some of the experiments that I did. And how did we do this? We annotated a lot of blog articles. We did statistical modeling, which is expectation maximization based. And then we also tried deep learning. And deep learning was mostly used to generate summary outcomes. Not sure if people here are familiar, but GPT-3 is one of those OpenAI recent models that can actually generate a summary based on a dialogue or based on a textbook. So we tried some of these approaches to see if this can actually help. One of the challenges that we faced was that we wanted to evaluate the efficacy of the information extraction, and it was very complicated. I think Blue score is the standard, where everybody uses the number of unique things that the machine learning model extracted and how a human annotated it. But overall, the Blue score was something that we definitely used. But it was, from a domain perspective, it was very challenging because we did not know how to evaluate the outcome. Should we consider it a success if the model was able to extract everything from a given document? Or should we consider it a success if the model was able to extract it from exactly that given sentence where the human also annotated? So we had to come up with a bunch of custom evaluations as well. So with all of this, we actually had an interesting approach of coming up with the unstructured data or extracting information from unstructured data. And I think the score now is, Clippy's already won, my bad. SkyNet -1 and +0.5. But for this case, Clippy was 0 because the traditional statistical models did not do well at all. The SkyNet model, which was or the one that we really thought would do very well in terms of extracting all the entities and relationships, it was not that efficient for that particular purpose. But however, generating summaries, so the deep learning model was really good at generating summaries. So I give a plus 0.5 for that, just because it can generate good summaries. So just in case you want a quick glimpse into what the alert looked like, if you're an analyst and you just wanted to triage that, and if you read that summary, okay, if that worked, great. So for this particular instance, the simpler models did not work. The more complicated models were we were asking beyond state of the art at that point. And then we got a good summary, so plus 0.5 for that. I think, as you can see in the slide I mentioned, it is difficult for the model to disambiguate between, a honeypot. These are the language models that are trained on Wikipedia articles, textbooks. All these are huge models that are trained. So it was difficult for the model to figure out a honeypot from Winnie the Pooh and in the context of a honeypot that's found in a security blog. So that was really a challenge. And of course, from an operational perspective, the amount of engineering that's needed to bring in these large models, the cost obviously is one of the biggest considerations in a security operations center. How much does it cost? How much would it cost to train these models, maintain these models? So these are other engineering aspects that I'm not even touching in this talk, but that is definitely one other thing. And is it really adding value? Is it incremental value? Is it not incremental value? Is it really worth it? Can't we just solve this with a simpler solution? Can't we just do regex? So I think all of those are valid here. Oops. All right, did I get the right one? Okay, yeah. Yeah, and I think now we're coming to the part where we wanted to talk about, or where I wanted to talk more about how how we can improve some of the operational efficacy aspects. So this is an example where we can actually help with threat hunting by dwindling down the data. So here we're trying to hunt for the malicious PowerShell commands in an ocean of PowerShell commands. And this was an unsupervised approach. This was slightly different from everything that we've seen so far, which are supervised approaches. This was an unsupervised approach. And the challenge here was that no analyst would go and label a PowerShell command and say that this was a malicious PowerShell command that was running. Nobody would do that. So we did not have a lot of labeled data. However, the unsupervised machine learning approaches that we used were still very relevant, especially when it came to clustering. What it did was it would definitely cluster a lot of similar looking PowerShell commands. And the pattern that emerged here was that we saw a pattern with a lot of PowerShell commands that you would typically expect to see in your network and in your environment. Again, here, the knowledge of what you have or what you would consider normal in your environment becomes critical. But this can definitely help someone in threat hunting, right? Because you know that once these PowerShell commands get clustered, you can probably see that some of these clusters are completely legitimate, that these are something that you would expect to see, and some of these are simply not. And a lot of these things are really helpful in pivoting when you're doing threat hunting, as well as trying to reduce the amount of data. The other one is, I think this everybody is or has heard of it at least once, because everybody talks about alert fatigue for the SOC analyst, and everybody would like to reduce the prioritization or like bubble down the low priority alerts. For this experiment, we had alert data with labels. We had alerts from different vendors, different data types. And we used both supervised and semi-supervised machine learning. The challenges here were also, the lack of label data and identifying the drift in priority. So for example, today, a particular alert type with a particular number, with a particular event was high priority, but 3 months down the line, that was not. And I think a lot of this boils down again to the policies that are very specific to a given organization as well as the risk. So how do we typically solve these problems, right? Like when we don't have labeled data, we try and get proxy labeled data. And how do we do this? We try to get these labels from the actions and the workflows that the SOC analyst takes. So in the end, if they close it, or in the end, if the SOC analyst says that this is something that I escalated further, then it's perhaps investigation worthy, perhaps something that needs to be bubbled up and not bubbled down. So these are some of the proxy labels that we could get. And another challenge was, how does the model remember? Is it memorizing what the analyst is saying, or is it actually objectively telling whether something is a threat or whether something is a priority or not? And I think that's a very difficult question to answer. And most of the current models, they typically learn from the humans, so they can do as good as the humans do. And if, in order to go beyond that, there needs to be other ways in which we have to approach this problem. So another interesting part here was that we tried to do a lot of gamifying also to kind of get labels. We had some interesting pop-ups that came up here that said, you're only like 10 points away. This is like the Uber ride level. So we kind of had something similar to that as part of the gamification experience for the SOC analysts. So over here, both the models that we used as part of the PowerShell clustering as well as for the alert prioritization, both the models we used were very simple traditional machine learning models, no deep learning, so Clippy gets 2 again. And SkyNet minus 0.5 here, because we did try one of those word embedding models that are commonly used in deep learning, where we try and train the model based on what it thinks are similar, and it provides a score. And this was very interesting. So the similarity of, say, something that was virus detected and virus blocked, the semantics of them is completely different. One, the virus detected means, OK, you have detected it, and virus blocked means, OK, you have detected and blocked it. So the action that somebody would take would be completely different here. And in this case, it was very interesting to see that it was the exact same similarity, so probably did not quite learn much. So now let's shift gears a bit. So we saw that most of the times Clippy is good enough for the current use cases that we're targeting. And what do we really need in order to successfully deploy or successfully bring any data-driven solution for security? Obviously, the people. One of the things that I notice when I'm interviewing others also, or when I'm getting job requisition descriptions, I notice that the description requirement or the job requirement for somebody who's a data scientist is security is a bonus point. You need to know how to engineer, mine large-scale data, and you need to write production code. So this is one set of job descriptions that I've seen. The other set of job descriptions that I've seen is you need to do data science, figure out how support the product management as well as the customer success teams to figure out how much of these models are being adopted. So it looks like there's a lot of ask. It's a huge ask, you know. And I think I'd like to borrow one of the lines from Joshua Neal from Securonics. And he says, build full stack teams, not full stack data scientists. It's extremely difficult to become a full stack data scientist. So another aspect is if you are looking to start a security machine learning program, a statistician or an ML engineer shouldn't be your first hire. Your first hire should be somebody who is a data architect who can work with the security teams to identify what kind of data sets need to be curated, how to govern those data sets. I think those are some of the things that we really need to look into. And then cross-train your statisticians and security practitioners. I can give you an example. So when training one of these models, the data scientists totally, as part of the feature engineering process, they completely omitted or basically gave a wildcard for the IP address, and everything else was modeled. If a security professional was there and was advising the data scientist, then the security practitioner would have immediately said that this will not work. This is exactly the kind of loophole that that an attacker would leverage to change the decision of the model. So try to cross-train. And then processes. I cannot emphasize this much. I think a lot of places where I've been, the first things that I get asked is, we want you to build a machine learning model that will help us catch APT28. And I think we're far away from that. I don't think we want to build a machine learning model that will catch APT28 right off the bat. I think that's not a realistic ask. So definitely try and work with your security teams, work with your leaders, set expectations. And if you are an enterprise security team, try to use the data that you already have. Try to leverage the workflows and the process that you do. Try to leverage that for data-driven approaches. Instead of starting new tools, instead of starting new processes, try to leverage the existing ones. And I think another point that I've noticed in a lot of data science teams is that data science teams are sometimes forced to fit into an agile framework. And it works in software engineering because you know the kind of problem you want to solve, you know what kind of solution there is, so you can work on it that way. But with data science, I've noticed that people say, oh, I want to solve this problem. I want to catch APT29. Maybe your data does not support it. You cannot really catch APT29. I want to solve user behavioral analytics, or I want to detect insider threats for trading my stocks. I think that is something you'll have to look into and set expectations only after looking at and exploring the data. From a technology perspective, I think it's, again, one of the things that's often overlooked is the MLOps practices. How do we harden the systems? How do we make them robust? And data scientists often forget their baselines. They try to go for the moonshots. Let's use the latest cutting edge, but we totally forget our baselines. Can we really improve on these baselines, whether these are rules-based or statistics-based? Can we really improve these? And lastly, this is the good, bad, and the ugly. So just summarizing everything that I mentioned here. I think the good part is, I think more mature security teams and data science teams, they actually work together, and they're trying to find that problem and solution match quality. They're trying to find that fit. And Occam's razor actually works. Start with the simplest problem for which you have the data. There are some really cool advancements also that are happening. So I think the security community has to keep an eye out on all the advancements that's happening in the AI and machine learning space. Maybe now is not the right time to try them and try to bring them into production, because they're definitely not battle ready or battle tested. So it's important. There is a lot of interesting work that's going on there. And with a lot of research and proper development and the right guidance, I think there is a lot of potential to use these advanced machine learning and deep learning models. And another thing is, in general, we're always focused on finding the threat, which is the needle. And we really don't have that magnet. So instead, maybe the approach should be, let's eliminate all the noise. Let's remove the haystack, and then the needle will automatically reveal itself. So maybe we have the tools to get the haystack, not the needle. So let's remove the haystack. The bad parts that I've noticed is the return on investment is inversely proportional to the model complexity. And this is an engineering challenge that needs more resources. I think most folks are interested in trying to build the latest models and not quite as interested as getting the engineering effort in place. So that's definitely one thing. And the mismatched expectations, right? Everybody wants to work on the latest and greatest, but very few things would actually work. So it's really hard to retain those data scientists who can work in security. They all want to go build recommendation engines and generate ads so that people can click on the ads. And I think the other bad thing is, again, let's focus on hardening. This is one of my pet peeves, the ugly part. There's not a lot of open research. I wish the community does more open research, share more data sets, share more code, and that way we can all test each other's models, determine what is actually valuable, what can be improved, how it can be improved. I think that there needs to be more push towards open sourcing the models as well as the data sets within the security community that works for security. Yeah, that's it from me, and I think now's the time for questions, if any. Yes. Sorry, the question was, do we see adversaries using machine learning and? Oh, great question. Yes, adversarial machine learning is a whole space in itself, and that is something that I definitely did not touch today. I only spoke about the defensive aspects. Adversarial machine learning is a thing. This is where there are a lot of different kinds of attacks. So for example, I think in the news most prominently you see autonomous cars that are misreading some signs because the machine learning decision boundaries are different. You also see data poisoning, right? How somebody could actually poison the data on which the model is trained. So you're poisoning it in the initial part. This is akin to the supply chain attacks that we see. Can we detect it? There are a couple of tools that are being developed. This is mostly for data scientists to make their models more robust so that they don't get attacked this way. So we're trying to be more proactive. In terms of detection, it's really difficult to say whether something looks like a normal request to a machine learning model that is hosted in the cloud. You could just send an API and you can get a response. And it's really difficult to know whether somebody's actually trying to trick the model. And traditional detection approaches would apply here as well. Look at the rates at which they're requesting for these predictions, and look at the kind of data points that they're requesting it for. Are they within each other? Because that's when you can infer that they are trying to infer the decision boundary of the model. Yeah, does that answer your question? Okay, no worries. Any other questions?